Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. You have some information here about the resources I offer for studying for actuarial exams. I direct the actuarial program at Illinois State University. Information about it can be found at smarturl.it/actuary. And if you would like to make a tax-deductible donation to our program to help our students, go to smarturl.it/help-ISU-actuary. Here's a problem for today, problem for exam MFE. Assume the Black-Scholes framework. Consider a 9-month at-the-money European put option on a futures contract. You are given that the continuously compounded risk-free interest rate is 10%. The strike price of the option is 20. The price of the put option is 1.625. If 3 months later the futures price is 17.7, what is the price of the put option at that time? Well, under the Black-Scholes framework, using the same approach as we use for stocks, but in this case for futures, it's a put option on futures contract. The put price formula is the present value of exercise price times n of minus d2 minus the what you could consider the prepaid forward price version for the futures contract that we are analyzing. You would have normally here S times e to the minus delta t, where delta is the dividend yield continuously compounded. So this f e to the minus rt replaces that, times n of minus d1, and d1 is very much like the standard Black-Scholes formula with the stock there, because for the stock it's the natural logarithm of s e to the minus delta t divided by k e to the minus rt. But because e to the minus rt appears in both terms, you can also remember this simply as ln of f over k plus 1/2 sigma square root of t, sigma squared times t divided by sigma square root of t. And d2, as always, is d1 minus sigma square root of t. The underlying price is the same as the exercise price. Option is at the money, so then that natural logarithm of f over k is the natural logarithm of 1, so it's 0. And the other data for the initial situation, 9 months before expiration, which is when f is equal to k as well, is that the price of the put is 1.625, risk-free interest rate continuous compounded is 0.10, time until expiration is 3/4 of a year or 9 months, but in years that's 0.75, and k is equal to f is equal to 20. So at that time, 9 months before expiration, we plug all the data that we know in, and we get d1 and d2 expressed in terms of sigma, which is not known. We need to find it. But the put price is given, so we can use the put formula, plug it all in, and what we get is an expression that says basically 1.625 is equal to 20 times e to the minus 0.075 times 2 times the cumulative distribution function of the standard normal distribution evaluated sigma over 2 times square root of 0.75, and then 1 is subtracted from that whole expression. Well, then we can figure out what n of sigma over 2 times square root of 0.75 is. Again, this is the cumulative distribution function of a standard normal distribution, and it's approximately 0.54378904. So you can use the normal distribution calculator and find then sigma over 2 times square root of 0.75 to be approximately 0.10998419, or look it up in the table that is given in the paper and pencil version of the test, and you will get almost exactly the same number, 0.11. And then sigma from that can be found to be that almost exactly 0.11 or 0.10998419 times 2 divided by square root of 0.75. So sigma is approximately 0.253999761. After 3 months, which is also 6 months till expiration, we'll have the following data. The F will be 17.7, that's given in the problem. T will be 0.5, 6 months till expiration. Sigma is what we just found it. R is still 0.10, K is equal to 20. That's the exercise price of the option. So we can find D1 but just by plugging in these numbers, and D2. And the put price is 20 e to the minus 0.10 times 0.5. So really e to the minus 0.05 times the normal distribution, cumulative distribution function evaluated at minus D2, which is 0.770094, minus 17.7 times e to the minus 0.10 times 0.5, which is 0.05, times n of minus D1, which will be 0.90406. And then just evaluate this either by the normal distribution values. There is a normal distribution calculator on the test that you can use, or look it up in the table in the paper version, and you get almost exactly 2.66, which is exactly, well, 2.66 is exactly answer D, so we get answer D. Please remember this is copyrighted material. The problem belongs to the Society of Actuaries. Society of Actuaries is the source of it. It's reproduced with permission, but the solution is mine. Good luck in your studies and good luck on the test.